Hey guys, what's going on? I'm bored as I have 45 minutes left. Hey guys, welcome. Today I'm doing a tutorial on communicating sequential processes. So today I'm going to be covering three topics, which are processes, concurrency, and non-determinism. So the first topic here is processes. What is a process? A process is a behavior pattern of an object with limited set of events selected as its alphabets. So a process is basically made up of events and alphabets. What are events and alphabets? Events are made up of alphabets, and events are nothing but the functions or actions executed inside a process. Symbolic notations of events, alphabets, and processes. Each of them have different symbolic notations. So the events are denoted in lowercase letters, and the processes are denoted in uppercase letters. And the alphabet of a process P is denoted as alpha of P. So, for example, here we have a vending machine, which is a process, and the alphabets of that process are coin and chocolate. Prefix X be an event and let P be a process, then uh, X then P is denoted as follows. For example, first example, we consider a simple vending machine which consumes one coin before breaking. So we have an event coin and we have a process of stop VMS. So after a customer inserts a coin, the vending machine stops, or it breaks, stops working. In the second example, we have a simple vending machine that successfully serves two customers before breaking. So we have a event coin here, and the right side of the coin event is a process. And after the coin event is executed, the next event chocolate is will be executed, and the right side of that is another process. So basically, the left hand side denotes the events, and the right hand side denotes the process. So here the customer first inserts a coin and receives a chocolate from the vending machine, and then again the second customer inserts a coin, and then again he gets the chocolate, and after that the vending machine stops working. So here, after serving two customers successfully, the vending machine stops working. Recursion. It, as we saw earlier, we had repetitive events occurring inside the process. So it would be extremely tedious to write out full behavior of a vending machine for its maximum design life. So we make use of recursion to represent repeating events. For example, we consider the vending machine. The tasks or the events which are unique for the vending machine is inserting a coin and the vending machine dispensing the chocolate. So this can be represented as follows, like the event coin, and then the event chocolate, and then the vending machine goes back to the initial state. Choice. Many objects allow their behavior to be influenced by interaction with environment within which they are placed. So if X and Y are distinct events, then X then P choice, Y then Q describes an object which initially engages in either of the events X or Y. So we have an event X and we have which is related to the process P, and we have an event Y which is related to process Q. So these two are separate events, and it, uh, it, so either one of the events are will be executed from either P or Q process. So we have a choice between two events or between two processes. For example, let's consider a machine that serves either chocolate or toffee on each transaction. This can be written as vending machine is equal to function which in which the coin is inserted, and we have a choice between the events chocolate and toffee, and then the vending machine goes back to the initial state. So if B is any set of events and P of X is an expression defining a process for which for each year different X in B, then X from B, then P of X defines a process which offers a choice of any event Y in B and then behaves like P of Y. So the denotation represented above should be pronounced as X from B, then P of X. Mutual recursion. Mutual recursion is nothing but recursion between two choices. So let's look at an example here. So here we have a drink dispenser, and we have two processes, orange and lemon. So the alphabets are common between the three processes, and the alphabets are set orange, set lemon, orange and lemon. So the drink dispenser gives us two events choice. So the first choice is set orange and the second choice is set lemon. So when the customer selects the set orange, the orange process is initiated, and when he selects set lemon, the lemon process is initiated. So when either of them is selected, either the orange or the lemon process, we have set of event choices between the events in the processes orange or lemon. So in case of orange, the customer can select orange and he gets the drink, and then the state goes back to the process goes back to the initial state, and then he has the second choice of event set lemon, where he can change the process from orange to lemon, so that he will be able to select lemon in after that. And then he has another option set orange, which doesn't change the state of the process. Similarly for lemon, he has again three options: lemon, which dispenses a lemon drink and then it goes back to a lemon process, and then the other two options are set orange and set lemon. Pictures. So to represent the processes and events, we can use the pictorial representation of a process by representing it in a tree structure consisting of circles connected by arrows. So here the circle represents the state of the process, and the arrows represent the transition between states. So for example, here we have three scenarios. In the first example, when the customer inserts the coin, and the state transition occurs and it goes to a next state. So the second example shows sequence of events of the vending machine serving two customers successfully. And the third example represents the complicated vending machine which offers the customer two choices of chocolate and toffee. Picture cannot represent infinite number of states. It's very hard to draw each and every event using pictorial representation. So we use of recursion to represent the uh, as shown in the figure in the example. So we have a vending machine which offers two choices, and then after dispensing either of them, the vending machine goes back to the initial state. This can be represented by giving a transition to the initial state. Similarly, the example 5 shows the sequence of events being executed, and after the final state is occurred, the transition goes back to the initial state. Trace. A trace of the behavior of a process is a finite sequence of symbols recording the events in which the process has engaged up to some moment in time. A trace will be denoted as a sequence of symbols separated by commas and enclosed in angular brackets. This is shown below. So here we have x, y in angular brackets consisting of two events x followed by y. So the two events are the traces here. And next we have x in is a sequence containing only event x, and the trace can also be an empty sequence of no events. So for example, a trace of a simple vending machine at the moment it has completed service of first two customers. So after the vending machine serves the two customers, the two events which have occurred will be coin chocolate, which are represented as follows. Operations on traces. So there are few operations on traces. The first one is concatenation, used to concatenate. It constructs a trace from a pair of operands s and t. It is denoted as shown below. Next we have restriction. The expression t restriction a denotes the trace t when restricted to symbols in the set A. So we can restrict the trace t by using any set A. Here we have an example of around, up, down, around. Restriction to up and down. So we get the events up and down from it. The next operation we have is head and tail. This is nothing but a complementary event traces. So if S is a non-empty sequence, its first sequence is denoted as S naught, and the result of the of removing the first symbol is S dash. So for example, here we have X, Y and X events equal to X, and this the complement of that or the tail of that head will be X, Y, X dash is equal to Y, X. So the next operation is star. It is nothing but a set. A star it is a set of all finite traces. Length. The length of the trace t is denoted by hash t. So the number of events in the trace is given by the length. For example, hash x will be giving the length 3, and empty trace sequence will be giving a length of 0. So the next topic here we have is concurrency. When two processes are brought together to evolve concurrently, the usual intention is that they will interact each other. So when the two processes P and Q are the processes with same alphabets. So the process P contains the same alphabets as of process Q, then it is represented as P concurrent Q. Denotes a process which behaves like the system composed of processes P and Q interacting in lockstep synchronization. So This is nothing but the process P and Q will be interacting with each other concurrently. So, for example, let's consider a scenario where of the vending machine which gives the customer two options. It either dispenses toffee or dispenses chocolate. So, let's say that we have a greedy customer who doesn't want to pay for the uh, toffee or chocolate. So, he only wants the vending machine to dispense the chocolate or the toffee. So in this scenario, uh, he either has choice of getting toffee or chocolate, or he has to insert coin and get the chocolate. But the vending machine from the first scenario does not dispense the item before without the customer inserting the coin. So in this scenario, he has to insert the coin, but when the customer inserts the coin, he will not want to get the item later on. So this is represented as greedy customer uh, concurrently interacting with uh, vending machine, and this is represented as a function of x coin and the sequence of events coin chocolate and the process going back to the same state. So the next we have here is pictures for concurrency representation. A process P with alphabet A, B, C is pictured in the box labeled P, from which emerge a number of lines. So in the figure 2.1 we see that a process P is represented in a box and there are three lines coming out of it, which are A, B and C, and we have another process Q which have three more lines B, D and C. So here we observe that the lines B and C are common in the processes P and Q, and the lines A and D are unique for each individual processes. So when two processes are put together to evolve concurrently, the resulting system may be pictured as a network in which similar labeled lines are connected, but lines labeled by events in alphabet of only one process are left free, which means that the common lines B and C are connected as shown in the figure below, and the lines which are individuals to the event processes are uh, A, which are A and D, are left free. So the next topic we have here is non-determinism. The non-deterministic or deterministic. So let's say we have two processes P and Q. Then we introduce the notation P or Q to denote a process which behaves either like P or like Q. So the alphabets of operands are assumed to be the same. So the alphabets of P or Q will be either same as alphabets of P and same as alphabets of Q. For example, a change giving machine which always gives the right change in one of the two combinations. So, a change giving machine which dispenses the change for 5 dime uh, for a dime, it either it takes the input of 5 paise and then outputs either the between the sequence of events of choices of outputting 3 1 pennies and 1 2 penny and then going back to the initial state, or in the output it outputs 2 pennies and 1 penny and goes back to the previous state. So here the customer has no way of knowing whether the vending machine is going to output the first sequence of events or the second sequence of events. So it is non-deterministic for the customer to know the outcome or the result